We're not going to go into more detail on multinomial regression now. What we're going to do is tell you about a different classification method, which is called discriminant analysis, which is also very useful, and it approaches the problem from a really quite different point of view. In discriminant analysis, the idea is to model the distribution of X in each of the classes separately, and then use what's known as Bayes' theorem to flip things around to get the probability of Y given X. In this case, for linear discriminant analysis, we're going to use Gaussian distributions for each class, and that's going to lead to linear or quadratic discriminant analysis. So those are the two popular forms. But as you'll see, this approach is quite general, and other distributions can be used as well. But we'll focus on normal distributions. So what is Bayes' theorem for classification? So it sounds pretty scary, but not too bad. So of course, Thomas Bayes was a famous mathematician, and his name now today represents a burgeoning subfield of statistical and probabilistic modeling. But here we're going to focus on a very simple result, which is known as Bayes' theorem. And it says that the probability of Y equals K given X equals X. So you've got, the idea is you've got two variables. In this case, we've got Y and X. And we're looking at aspects of their joint distribution. So this is what we're after, the probability of Y equals K given X. And Bayes' theorem says you can flip things around. You can write that as the probability that X is X given Y equals K. That's the first piece on the top there. Multiplied by the marginal probability or prior probability that Y is K. And then divided by the marginal probability that X equals X. So this is just a formula from probability theory. But it turns out it's really useful and is the basis for discriminant analysis. And so we write things slightly differently in the case of discriminant analysis. So this probability Y equals K is written as pi K. So if there's three classes, there are going to be three values for pi, just the probability for each of the classes. But here we've got class little k, so that's pi K. Probability that X is X given Y equals K. Well, if X is a quantitative variable, what we write for that is the density. So that's a probability density function for X in class K. And then the marginal probability of X is just this expression over here. So this is summing over all the classes. Okay? And so that's how we use Bayes' theorem to get to the probabilities of interest, which is Y equals K given X. Now at this point, it's still quite general. We can plug in any probability densities. But now what we're going to do is go ahead and plug in the Gaussian density for f sub k of x. Before we do that, let me just show you a little picture to make things clear. In the left-hand plot, what have we got here? We've got a plot against x, single variable x. And in the vertical axis, what we've got is actually pi sub k and multiplied by f sub k of x. For both classes, k equals 1 and k equals 2. Now in this case, so remember in the previous slide, the probability was essentially proportional to pi sub k times f sub k of x. And in this case, the pi's are the same for both, so it's really to do with which density is the highest. And you can see that the decision boundary, or the vertical dashed line, is at 0. And that's the point at which the green density is higher than the purple density. And so anything to the left of 0 we classify as green, and anything to the right we classify as purple. Okay? And it sort of makes sense that that's what we do there. The right-hand plot has different priors. So here the probability of 2 is 0.7 and of 1 is 0.3. And now, again, we plot in pi sub k times f sub k of x against X, and that bigger pie has bumped up the purple. And what it's done is moved the decision boundary slightly to the left. And that makes sense too. Again, it's where they intersect. It makes sense as well, because we've got more purples here. Actually, I say they're pinks. It looks purple to me. There's more of them, so everything else being equal, we're going to make less mistakes if we classify it to purples and to greens. Okay, so that's how these priors and the densities play a role in classification. Okay, so why discriminant analysis? It seemed like logistic regression was a pretty good tool. Well, it is, but it turns out there's a room for discriminant analysis as well. And so there's 3 points we make here. When the classes are well separated, it turns out that the parameter estimates for logistic regression are surprisingly unstable. In fact, if you've got a feature that separates the classes perfectly, the coefficients go off to infinity. So it really doesn't do well there. Logistic regression was developed largely in the biological and medical fields, where you never found such strong predictors. Now, you can do things to make logistic regression better behaved, but it turns out linear discriminant analysis doesn't suffer from this problem and is better behaved in those situations. Also, if n is small, the sample size is small, and the distribution of the predictors x is approximately normal in each of the classes, it turns out the linear regression discriminant model is again more stable than logistic regression. And finally, if we've got more than 2 classes, we'll see logistic regression gives us nice low-dimensional views of the data.
And the other point, remember, in the very first section, we showed that the Bayes rule, if you have the right population model, the Bayes rule is the best you can possibly do. Right, so if our normal assumption is right here, right, then this Bayes rule from discriminant analysis from the Bayes rule is the best you can possibly do.
Good point, Rob.